ম্যাম চ্যাট বক্সে অরিত্র লিখেছে ওর মাইকটা কাজ করছে না।
ক্লিয়ার করা যাবে।
রোল নাম্বার 05।
So the next module or chapter 2 is on root locus technique. Root locus technique is a graphical tool which is used for analysis as well as design purpose. Right? So already we have studied stability, notions of stability, concepts of stability, as well as what is meant by absolute stability, Raut-Hurwitz stability, criterion, etc. So we know that given a system, our first task is to find out or to investigate the stability of a system. So if we find that the system is not stable, then by some means we'll have to make the system stable. Otherwise, we won't be able to work with the system because we can't work with an unstable system. But at times we find that yes, the system is stable, but its response is not satisfactory. Like, say, we may find that the damping ratio, you have studied second order systems, you know what is damping ratio, natural frequency, etc. So it might so happen that the damping ratio of the system is very poor, very low. So what will happen? The system will exhibit a long damped oscillation before coming to steady state. So the system will behave like a very slow system. The response of the system will be very sluggish, right? And the settling time, obviously, the settling time will increase, and such a system is not really desirable or acceptable so far control systems are concerned. So generally we prefer a fast system. So that's why the response of the system will find that it's not acceptable. So after ascertaining the stability of the system, we'll have to analyze the system and we'll have to find out whether the performance of the system is acceptable or not. If the performance is not acceptable, then we'll have to adapt some means by which the performance of the system can be improved. Okay. Now, for a second order system, we know that the speed of the response is directly related to the locations, particularly for underdamped system, not undamped, sorry, underdamped system. The speed of the response is directly related to the locations of the complex conjugate pole pair of the system. Do you agree? Do you agree? Statement is for an underdamped second order system, the speed of response is directly related to the locations of the complex conjugate pole pair of the system. Do you agree? On the S-plane, certainly. Underdamped system means the roots of the characteristic equation will be complex conjugate pole pair, and the locations of the complex conjugate pole pair will dictates the damping ratio of the system, and on the damping ratio as well as zeta omega n. So the damping ratio and zeta omega n will give us the peak overshoot as well as settling time, etc. Okay, so from this we can conclude that in general the response of the second order system is related to the locations of the closed loop poles of the system on the S plane, right? Now, if we consider higher order system, the third order or fourth order, so for higher order system, we know that we cannot define damping ratio or natural frequency. So what can be done? An higher order system can always be expressed as an equivalent second order system. If we consider two dominant pole pair, that means closed loop pole pair, or roots of the characteristic equation to dominant roots of the characteristic equation, then a fourth order or third order or any higher order system can be represented as an equivalent second order system. So often, it's really difficult to study or to analyze a higher order system. So often, we simplify an higher order system and represent a higher order system with the help of an equivalent second order system. Do you get my point?
Yes, ma'am.
So if we can represent the system with the help of an equivalent second order system, again, we can associate the notions of damping ratio and natural frequency, and it's clear that the performance or the response of the system will be related to the locations of its closed loop poles on the S plane. Right? Now, if it's a higher order system, then what are the locations of the closed loop poles of the system on the S plane? If you want to find that out, then what we'll have to do? We'll have to solve the characteristic equation describing the system, right? Now, for a fourth order system, the characteristic equation will be a fourth order equation, or the characteristic polynomial will be a fourth order polynomial. For a seventh order system, it will be a seventh order polynomial. And suppose, or let's consider that to improve or to adjust the performance of the system, we keep one parameter of the system as a variable part. That means if we tune that variable parameter of the system, we assume that the system performance, obviously, if we change the variable parameter, if we change the variable, vary the variable parameter, the characteristic equation will change. Yes or no?
Yes, ma'am.
So naturally, the roots of the characteristic equation will also change. Yes or no?
Yes.
So that means by varying a parameter or tuning a parameter, we can alter the response of a system. So in such a system where a particular parameter of the system is variable one, and if you consider that the parameter is being varied over a wide region, say from 0 to infinity, then if you want to find out the locations of the roots of the system for each value of that particular parameter, then repeatedly we'll have to solve the characteristic equation for finding out the locations of the roots of the characteristic equation on the S plane. Do you agree?
Yes, ma'am.
So for a higher order system, this method of solving the characteristic equation is really very tedious, time consuming, and generally we don't adhere to this method, right? So, so a simple technique known as root locus technique for finding the roots of the characteristic equation was introduced by W.R. Evans. W.R. Evans. That's why the root locus plot, we'll see, as I see it, it's a graphical tool. We'll get a plot. Finally, we'll get a plot which we call root locus plot. And since it was introduced, it was developed by W.R. Evans. Often in some books, you might find that the plot is being called Evans plot, is extensively used in control engineering practice. This technique provides a graphical method of plotting the locus of the roots in the S plane as a given system parameter is varied over the complete range of its values. So, what is the meaning of this statement? What is the meaning of this statement? As we have discussed right now, that if we vary a system parameter, then the roots of the characteristic equation will the roots of the characteristic equation will vary, and hence the locations of the roots of the characteristic equation will change on the S plane. Yes or no?
Yes.
So let's consider one single root, right? So, so the first root. So if we vary the variable parameter over a wide range continuously with the variable parameter, the location of that particular root will change on the S plane. Do you agree? So that means we can say that each root of the characteristic equation will describe a locus, as the system parameter is varied over a wide range. Have you understood this? Right? So that means for an nth order system, n number of roots of the characteristic equation will describe n number of loci on the S plane as the variable parameter is varied over a wide range, right? So that's why the name of the tool is root locus technique. Clear? Have you understood this? Have you understood the basic concept of root locus technique?
Yes, ma'am.
So now the roots corresponding to a particular value of the system parameter, if we can sketch the complete root locus plot for the given system, we'll see how to do that. Then the roots corresponding to a particular value of the system parameter can then be located on the locus, or the value of the parameter for a desired root location. That means if we want to improve, if we want to alter the response of the system, then we'll have to choose the desired root location. And how can we achieve those desired root locations? We'll have to adjust the parameters. Then what should be the value of the parameter? That value of the parameter can also be found from the root locus plot. Once we sketch the complete root locus plot, then for a particular value of the parameter, the locations of the roots on the S plane can be found, as well as if we fix the locations of the roots of the characteristic equation, then what is going to be the value of the variable parameter, that can also be found from the complete root locus plot. Yes, do you have any doubt? Do you have any question? Okay. So let's discuss the basic concept. So we are considering a second order system, and see, this is the block diagram. So from the block diagram itself, it's clear that it's a unity feedback system. So HS is 1, and GS, the forward path transfer function, is given as GS, or we can write this as GSHS, the typical open loop transfer function. Try to recall open loop transfer function. So GSHS is given as K by S into S plus A, right? So this is a second order system. uh, and from the open loop transfer function, you see, we can find out the locations of the open loop poles on the S plane. Please note, I'm talking about open loop poles. This is the, again I repeat, GSHS is equal to K by S into S plus A. This is the block diagram. So from the block diagram, or if I write GSHS, that means we are actually considering the open loop transfer function. So this is our open loop transfer function. So the poles will be the open loop poles, and from this expression, it's clear that the system, being a second order system, has two open loop poles. One pole is located at the origin of the S plane at S equal to 0. The second pole, second open loop pole, is located at S equal to minus A, right? Now here we have not specified any value for this forward path gain K or this parameter, system parameter A. So in this, while we'll be discussing this system, we'll consider A to be a fixed one. Okay? And we'll vary this forward path gain K, as this is the most commonly used practice, and we have also discussed this while we have discussed route stability criterion. So here we'll assume that we'll be varying this forward path gain K over a wide region. That means we'll vary the value of gain K, say from 0 to infinity. Okay, now it's a second order system, so very easily we can find out the two roots of the characteristic equation, or in other words, the two closed loop poles of the system. So for that, we'll have to form the closed loop transfer function, which is Cs by Rs, and this is the open loop transfer function. So the closed loop transfer function will be Ts will be equal to K by S square plus As plus K. Okay, तो
Yes, ma'am.
so this is our closed loop transfer function. So this is the characteristic equation, S square plus As plus K equal to 0. So now we can solve for the roots, and obviously the roots will be functions of K. We are considering, again I repeat, A is constant. So the two roots S1 and S2 will be equal to minus A by 2 plus minus root over S square by 4, or A by 2 whole square minus K. Please check whether this expression is correct or not. We continue. Respond করো. So as I said, we'll be varying the value of gain K from 0 to infinity. Okay. So if the value of gain K is 0, then what will be the locations of the two closed loop poles? That means roots of the characteristic equation on the S-plane. What are the root locations when k is equal to 0?
0 minus A.
0 minus a. So if the value of gain k is 0, then you see the closed loop poles or the roots of the characteristic equation are same as the open loop poles. As already we have seen that the open loop poles are located at s equal to 0 and s equal to minus a. Okay, so when the value of gain k will be 0, the locations of the closed loop poles or simply the closed loop poles and the open loop poles will be same, right? Now, if we vary the value of gain k within this range, that means the value of gain k is greater than 0. Already we have considered the case when the value of gain k will be 0. So k greater than 0 and less than s square by 4. So what will be the root locations? Or rather, first tell me what will be the nature of the two roots?
Real.
Real, and the roots will be identical. Asking these questions because depending on the root locations, you see the system behavior starts changing. So within this range, where k is greater than 0 but two real and distinct roots, that means the second order system will behave like an over damped system. Am I correct?
Yes, ma'am.
And when the value of gain k will be equal to a square by 4, what uh, what will be the root locations? Two root locations. YOLO. When the value of gain k will be equal to a square by 4, root locations
Minus A by 2.
minus a by 2. That means if k is equal to a square by 4, the two roots are real but repeated in nature, isn't it?
Yes, ma'am.
So for a value of gain k which is equal to a square by 4, now the system will start behaving like a critically damped system. So you see the response of the system is varying with the value of gain k. And also it's very obvious that if the value of gain k exceeds this value, if gain k is greater than a square by 4, then we'll get two complex conjugate root pair, isn't it?
Yes, ma'am.
But you see, the whatever be the value of gain k beyond this value, a square by 4, if you go on increasing the value of gain k from uh, a square by 4 up to infinity, the real part of the complex conjugate pole pair will not change. It's fixed at minus a by 2. So the sigma part of the complex conjugate root pair are not sigma part is not affected by this value of gain k. Am I correct?
Ma'am, can you repeat?
So if the value of gain k exceeds the value is square by 4, so what will be the nature of the roots?
Imaginary.
Two roots will be complex conjugate, right? To be more precise, the roots will be complex conjugate, not really imaginary, because the real part is not zero. And what will be the real part? That means the sigma part.
Yes, ma'am.
What is the value of the sigma?
Minus a by 2.
Minus a by 2. So whatever be the value of gain k, if you go on increasing the value of gain k up to infinity, is the sigma part going to change?
Yes.
Sigma part will change.
No, 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 ma'am. A constant.
So sigma part is constant. You see, sigma part is not affected by the value of gain k, isn't it?
Yes.
So now, what we have observed or what we have discussed so far, let's try to plot our observation on the S plane. So this is our S plane, and remember, whenever you'll be sketching the root locus, since the root locus plot is one S plane based plot, you'll have to properly level these two axes. One is the real axis sigma, other one is the imaginary axis g theta, right? So when the value of gain k was zero, uh, we observe that the roots of the characteristic equation were identical with the open loop poles of the system, and one root is located at s equal to 0, the other root is located at s equal to minus a. So these are the two open loop poles. Am I clear?
Yes, ma'am.
And if k is equal to 0, this too will be the closed loop poles as well, right? Now, if we start increasing the value of gain k from 0, but if we keep the value of gain k less than a square by 4, you see this particular root will start being more negative. The root will remain real, but it will become more negative. Am I clear?
Yes.
And this root, what will happen to this root? As k is increasing, this root will remain within that particular range. This root will remain real, but will start being less negative. You get this?
Yes.
So that means since both the roots are real, that means we can say that this root will start, the first root will start describing a locus with k, right? And as k is increased within that particular range, this root will start moving along this negative real axis in this direction, in the direction of this arrow. And this root, the second root, if I consider this root to be the second root will start moving or describing a locus again along the negative real axis, but in the opposite direction, in the direction of this arrow. Am I clear?
Yes, ma'am.
So this root will start describing a locus, this root will start describing a locus, and when the value of gain k will be equal to a square by 4, you see this two loci will meet at this particular point. And what is the value of this particular point? The value of gain k is a square by 4, and this point is a is equal to minus a by 2. Do you agree?
Yes. Yes, ma'am.
So these two loci are meeting at this particular point, right? And after that, if we increase the value of gain k further, so if the value of gain k exceeds this value a square by 4, these two loci will break away from each other, and one root will follow this path, or the locus of one root will be like this, and the locus of the other root will be like this, and this line will be a straight line parallel to the imaginary axis. Why? Since the real part, this part this part is constant, which is minus a by 2. Have you understood this?
Yes, ma'am.
So if you go on increasing the value of gain k towards infinity, this locus will move along this straight line towards infinity. This uh, locus will start moving towards infinity as k tends to infinity, right? So we have got two loci for two roots of the characteristic equation, as it's a second order system, right? And this complete plot is called a root locus plot. Now, till now I was using the term loci and locus. So I said that this is one locus, this is one locus, but in while we discuss with locus technique, we don't use the term loci. Okay? We use root branch. So this root will describe certainly a locus, but that is called a root branch, and this is the second root branch. So we are getting two root branches, and one root branch is moving like this. This is a real root branch, this is also a real root branch. Two real root branches are meeting at this particular point, and if we increase the value of gain k beyond this value, then these two real root branches will break away from each other and will form two complex conjugate root branches like this. Clear? So one, if we can draw, so this is our, and the plot itself, the complete plot. The complete plot is called the root locus plot. So for an nth order system, n number of root branches will be there, and the complete sketch will be called the root locus plot of the system. Now is it clear?
Yes, ma'am.
Now you see, already we have discussed, if we can sketch the root locus plot, it's very clear that whether the system is behaving like an underdamped system or an overdamped system, or is it whether the system is a critically damped system or not, that can be concluded simply by inspecting the root locus plot, right? Now also you see, this sigma part, this real part is equal to zeta omega n. Now, since when the system is behaving like an underdamped one, since this part, the real part, sigma part, is constant, hence we can conclude that the settling time for a particular band of the system will always remain constant. The settling time will not change, because the settling time is given by, for a particular band, it's given by either 3 by zeta omega n, or 4 by zeta omega n, or 5 by zeta omega n, etc. Now sigma is equal to zeta omega n. So since sigma is constant, hence the settling time will remain constant. Now, suppose if we want our roots, if we want the system to behave like an underdamped system, and if we want a particular damping ratio, then just joining this point, this angle will give us the damping ratio, isn't it? If I consider the root location to be this point, can you follow me? Let us consider that the root of the characteristic equation is located at this point, and the second root is the conjugate part of this. Then if I join this root with the origin of the S plane, then this angle will give us the information about the damping ratio of the system? Yes or no?
Yes, ma'am.
Right? So if we want our system to have a particular damping ratio, say 0.707, then we can place the roots on the root locus, and accordingly we can find out simply using simple trigonometry. We can find out the value of gain k. What should be the value of gain k if we want our system to have that particular damping ratio, right? Or if we find that yes, the damping ratio is this, so we can join the line and we can find the locations of the closed loop poles of the system. So that means what is the behavior of the system that can be analyzed with the help of this tool, as well as if we want to alter the behavior of the system, performance of the system, response of the system, then also you can use this particular tool. So root locus technique is a very popular design and analysis technique for linear system. Very, very important tool. So far what we have discussed, do you have any question? Do you have any question? It's very easy to solve the characteristic equation. And already we have discussed that for higher order system, this technique will not help. Right? So how to construct a loop locus in general, that we'll discuss next. Now, we know that the characteristic equation delta S, please note down this equation. Right now, you'll not be able to appreciate this equation, you will not be able to understand this equation. When we'll discuss signal flow graph, then you'll be able to understand this particular equation. So for the time being, please note down this equation, and beside the equation, please write down wide signal flow graph, chapter 4. We'll discuss signal flow graph in chapter 4, in the fourth chapter. Do it fast. Done?
Done, ma'am.
Okay. So you see, this equation can be written in a compressed form as 1 plus Ps is equal to 0. 1, the entire thing, all these P's combined together can be represented as Ps. Okay, so this equation in a compressed form can be written as 1 plus Ps is equal to 0. So this is the characteristic equation for a multi-loop system. Multi-loop system means more than one feedback path. Okay. Now for a single loop system, when there is a single feedback path, so please note, for a single loop system, this equation is a familiar one, and this PS can be replaced by this term GSHS, where GSHS is the open loop transfer function. So this expression is pretty known to us. So the characteristic equation for a single loop system is 1 plus GSHS equal to 0. Now, okay, for the timing, we are considering this to be the characteristic equation, and PS is GSH is for single loop system. Have you written down this equation? 1 plus PS is equal to 0.
Yes, ma'am.
So 1 plus PS is equal to 0 means PS will be equal to minus 1. PS is equal to minus 1,
Yes.
right? Right? Now, AS is a complex quantity, hence, you see, this equation can be broken down into two equations. What are those two equations? The first equation is magnitude, since AS is a complex quantity, hence P, which is function of AS, will also be a complex quantity. So it will have its magnitude as well as its phase angle, right? So this equation can be broken down into two equations, and the first equation is magnitude of PS will be equal to 1. Clear?
Yes, ma'am.
And the angle part, you see, because of the presence of this minus sign, angle of PS, angle of PS will be plus minus 180 degree into 2q plus 1, where q is any integer. You could assume values like 0, 1, 2, 3, etc. Right? So, why this? Because we know that because of this minus sign, the angle of PS will be minus 180 degree or plus 180 degree or odd multiples of plus minus 180 degree. Yes or no?
Yes.
So now we can write angle of PS is equal to plus minus 180 degree 2q plus 1. Since q is one integer, so 2q plus 1 will be an odd number. So angle of PS will be odd multiples of 180 degree. Have you understood this? These two equations?
Yes, ma'am.
So the first equation where we are writing magnitude of PS is equal to 1 is called magnitude criterion. Quite obvious. And the second equation where we are getting the phase angle of PS is called the angle criterion. So magnitude criterion is magnitude of PS will be equal to 1, and the angle criterion is angle of PS will be odd multiples of plus minus 180 degree. Now, are you taking down notes or should I continue? Which the angle criterion is satisfied. In other words, root locus will pass through the points on the S-plane at which this angle criterion is satisfied. Here, for the time being, we are not discussing anything about the magnitude criterion. Later, we'll see that when and where magnitude criterion is required, but to find out the roots of the characteristic equation, on the S-plane, only the angle criterion is sufficient. Okay, so if we take any arbitrary point on the S plane, and if at that particular point we check the angle criterion, and if we find yes, the angle of PS at that point is indeed all odd multiple of 180 degree, then and then we can conclude that that particular point is a root of the characteristic equation, okay, for a certain value of gain k. And since the point is the root of the characteristic equation, hence the point will lie on the root locus of the system, or we can say that the root locus will pass through that particular point. Got it?
Yes, ma'am.
Okay. So I'm not discussing this particular example. Please go through this example. And the example shows that yes, if we apply angle criterion is sufficient for finding out the roots of the characteristic equation. And if you vary the value of gain k over a wide region from 0 to infinity, the angle criterion will result in the complete root locus gauge of the system. So this is the forward path transfer function. Hs is equal to 1 means unity feedback system. So this is the characteristic equation, 1 plus GHs is equal to 0. So now to check the angle criterion, we'll have to find out the angle of GS. In this case, PS is GS, right? So angle of GS, that means angle of this K is a gain, so it will not contribute towards the angle. So angle contributed by the open loop 0 and the angles contributed by open loop poles. So to satisfy the angle criterion, or for finding out the root locus, we know that this angle should be equal to plus minus 180 degree to q plus 1. So S is equal to sigma plus j omega, right? You substitute S by sigma plus j omega and find out the angles. So we know that the angle contributed by the 0, since the 0 is in the numerator, angle contributed by the 0 will be positive, and the angles contributed by all the poles will be negative. So angle contribution of the 0 will be tan inverse omega by sigma plus b. I guess you know all these things.
Yes, ma'am.
And the angle contributed by this term, which is sigma plus j omega, will be minus tan inverse omega by sigma, and angle contributed by the second pole at is equal to minus a will be minus tan inverse omega by sigma plus a, and that will be equal to minus pi, minus 180 degree. So just go through these steps, and finally you will find that the locus is basically a circle. So applying angle criterion, this example shows that we can sketch
Ma'am,
the root locus. Yes,
can you repeat why you're taking minus pi instead of any odd multiple of pi?
you can take that. The result will be same. This is
All right,
only
ma'am.
for making the calculation simple. Nothing else. So finally, you'll get the locus, which is basically a circle, and this is the sketch of the root locus. This two are the two open loop poles. This is the open loop 0, etc. And again, you can find out the center and the radius of the circle. Now, construction of root locus. Again, that was the second order system, right? For higher order system, again, we cannot construct the root locus applying this particular technique. Only we have discussed this particular example to establish the fact that angle criterion actually gives us the locations of the roots of the characteristic equation on the x-plane. So now how to construct the root locus actually. So this is our characteristic equation. Obviously we are considering the single loop system 1 plus GSH equal to 0. Now GSHs, so 1 plus GSHs, you see this GSHs can be expressed in time constant form or in this pole zero form, right? Now this form is more popular than the time constant form. Yes, if you express the transfer function in this form, you can obtain the transfer function in the pole zero form, or if you express the transfer function or obtain the transfer function in pole zero form, you can express the transfer function in time constant form. It's not difficult. But why I'm choosing this pole zero form? Because just try to recall the experiment uh, that we have discussed. The title of the experiment was identification of linear system. So if the system is unknown, we have seen that we can apply frequency response test, and with the help of the test, uh, we can obtain the transfer function, and the transfer function comes out in the pole zero form because we draw the asymptotic magnitude Bode plot. Can you recall?
Yes, ma'am.
And from the corner points actually indicates the locations of the zeros and the poles of the system, right? So that's why generally the transfer function is can be obtained or is obtained in pole zero form. So this is the conversion factor from k dash to k that you can always check. It's not difficult. So going back to this equation, so from this equation, it's clear that again, K product. Okay, one thing. You see from this expression, it's clear that number of open loop zeros is equal to M. ZI's are the locations of the open loop zeros, right? And I is varying from 1 to n. That means the system has m number of open loop zeros, and there's an nth order system, generic nth order system, and the system does have n number of open loop poles located at minus pjs. ठीक है?
Yeah, ma'am.
So this equation can be written as again this okay first this equation can be written as k into product of s plus zi's divided by product of s plus pj's is equal to -1. Again we'll break down the equation into two equations. Yes. Okay. So the first equation will be k into product of phasor lengths of the phasor constituted by the zeros, open loop zeros, or magnitude of s plus zi divided by product of magnitude of s plus pj's. So this magnitude will be equal to 1.
Yes, ma'am.
So this is our magnitude criterion. And what will be the angle criterion? The angle criterion will be the angle of GS, and that is the angle summation of all the angles contributed by all the open loop zeros minus summation of all the angles contributed by all the open loop poles. So that can be expressed as summation, and the variable is varying from 1 to m, angle of s plus zi is minus summation is varying from 1 to, it should be j. It should be j. J is varying from 1 to n, angle s plus pj's, and that angle should be equal to plus minus 2q plus 1 into 1 into dt. Clear? So this is our magnitude criterion and this is our angle criterion. Have you understood this?
Yes, ma'am.
So what have we discussed so far? If a point on the S-plane satisfies this angle criterion, then that particular point will be a root of the characteristic equation. That means the root locus of the system will certainly pass through that particular point. So how the root locus can be constituted, can be constructed? I'll come to this later. Let us consider a system having all these open loop poles and zeros. So we see there is one open loop pole at origin. This is the S plane. Don't forget to level this axis. Okay. So yes, there is a pole at origin. We uh, denote this pole as minus P1. It's just a convention. If we write minus P1, then the phasor will be S0 plus P1. And if we denote this pole by P1, then the phasor will be S0 minus P1. And two complex conjugate pole pair like this, one is P2, one is P3 at minus P2 at minus P3, and 1 0, just a hypothetical system at 0 at minus Z1. Now for such a system, we'll have to construct the root locus. How can we do so? Now let's take any arbitrary point on the S-plane, and that will be our trial point. Okay, we don't know whether the point is a root of the characteristic equation or not, or whether through that point the root locus will pass or not, or if a point on the S-plane is a root of the characteristic equation, or if, in other words, if the root locus passes through that point, then we call that point to be one on locus point. On locus point, right? And through a point, if the root locus doesn't pass, then the point will not be a root of the characteristic equation, and we'll call that point as not on locus point. Clear?
Yes, ma'am.
So let's take a trial point is 0. We don't know whether the trial point is one on locus point or not. So to find out whether this trial point is one on locus point or a not on locus point, we'll have to apply angle criterion at this point. So how to apply angle criterion at this point? You see, we'll have to construct this phasors. Okay, so this is the first phasor. We are joining this open loop pole and this trial point. So we are getting this phasor. This phasor is denoted by S0 plus P1, right? And this is the angle contributed by this phasor at this trial point. Or in other words, we can see that this is the angle contributed by this open loop pole at this trial point. Okay, and the length of the phasor, this is the length of the phasor. The length of the phasor will be the magnitude of the phasor. Agree?
Yes, ma'am.
Similarly, we'll construct rest of the phases by joining all the open loop poles and zeros to this trial point. So this is the second phasor. It's S0 plus P2, and if you draw this horizontal line, then this angle will be contributed by this open loop pole at this trial point. Similarly, we join this open loop complex pole to this trial point and construct this phasor. So this is the angle contributed by the phasor or by the open loop pole P3 at this point, and this is the phasor which actually joins the trial point with the open loop 0. So this is the phasor is 0 plus Z1, and this is the angle contributed by this open loop 0 at this trial point. Clear?
Yes, ma'am.
So now let's call this. Okay, fine. Okay, let's assume this angle to be theta 1. This angle theta 2, this is theta 3, this is theta 4. Now, since we have chosen this particular point A0, that means this point is known to us. Similarly, all the open loop poles and zeros, locations of the open loop poles and zeros are known to us because the open loop system is given. If the system is not given, you can't sketch the root locus plot, right?
Yes, ma'am.
So we can compute all these angles. How can we compute these angles? What could be the methods?
By angle criteria.
Hello? Of of the open loop poles and zeros are also known. So how can we measure, say for example, how can I measure this angle? Using protractor. তোমরা কি কোয়েশ্চেনটা বুঝতে পারছো না?
By the real part.
So with the help of trigonometry, can you use protractor? Yes or no?
Ma'am, please repeat. I can't hear.
Can we use protractor for measuring the angles? Can we place a protractor over here and measure the angle? Yes or no?
Yes.
No, we can't. Can't. Unless you take, it's very simple. Unless you take same scale. If you choose same scale on for both the axes, the measurement will be incorrect if you use protractor. You get my point?
Yes, ma'am.
So, yes, with the help of trigonometry, you can find out the angle. And any other method that you know? Simpler method? You don't know? You have your calculators with you? Do you have your calculators with you? Do you have buttons like rectangular to polar, polar to rectangular? Do you know how to do this conversion?
Yes, ma'am.
So if you construct this phasor, S0 will be some sigma 1 plus some j omega 1, isn't it? Sigma 1
Yes,
value
ma'am.
is known, j omega 1 value is known. Similarly, if I consider this open loop pole, the pole is known. So for this sigma 2 plus j omega 2, known, right? So you can write the phasor in rectangular form, and if you just convert it into polar form using rectangular to polar conversion, you will simply get the phase angle. You get my point?
Yes, ma'am.
So you don't have to apply trigonometry, you don't have to do all those things. Just simply by rectangular to polar conversion, you can measure these angles. And don't ever use protractor. Anyway, so theta 1 minus theta 2 minus theta 3 minus theta 4 for this case, if that angle, if we call the total angle theta 1 minus theta 2 minus theta 3 minus theta 4 to be some theta, and if we find that yes, theta is equal to odd multiples of plus minus 180 degree, then this point will be one on locus point. This point will lie on the root locus. Is it clear?
Yes, ma'am.
Yes, ma'am.
And if the angle criterion is not satisfied at this trial point, then what we'll have to do? We'll have to shift the trial point either in this side or in this side or in this side and in this side. And again, at the next trial point, we'll have to repeat the same procedure to find out whether the second point is one onlookers point or not. Right? So in this manner, if we want to obtain a smooth representative root locus for a system, so on the S plane, at least will in this trial and error method, we'll have to find out at least 1000 to 1500 points on locus points. And if we join all those onlookers points with the help of smooth line, then we'll get the complete root locus gauge of the system. So the construction of the root locus is a trial and error procedure. So, okay. So in this way we can construct. So let's assume that this point is one onlookers point. Then what is the value of gain k at this particular point? What is the value of gain k at this particular point? We'll have to know that, otherwise our information will not be complete. So the value of gain k at this point, at a point on the root locus, can be calculated using magnitude criterion. Right? So the value of gain k will be, just look at this equation, So now S0 is S0, the trial point, we have assumed to be an onlookers point. So k will be, you see, this one divided by this one. So if we apply magnitude criterion at S0, then we can find the value of gain k. K is equal to product of j varying from 1 to n, phasor length of S0 plus pj's, and product of I varying from 1 to m, phasor length of S0 plus zi. So in essence, the value of gain k at a particular point on the root locus is product of phasor lengths. This is phasor. Product of phasor lengths from S0 to open loop poles divided by product of phasor lengths from S0 to open loop zeros. Here. So when we are using magnitude criterion, is that clear to you?
Yes, ma'am.
So now, if I ask you to follow this particular procedure, and if I ask you to construct the root locus for a given system using this particular technique, so will you be able to draw the root locus plot? Yes or no? What is the solution? The solution is to have 8 to 9 rules, very simple rules, with the help of which we can construct an approximate root locus for a system, given system. An approximate root locus for a given system, though it's not an accurate one, but the approximate root locus is a very powerful tool for analysis purpose of a system, a given system. Right? So approximate root locus is sufficient enough for analyzing the performance, the behavior of a given system. And often we just sketch manually using this construction rules. We sketch manually the root locus plot, and even we design, if required, we uh, use that approximate root locus plot for design purpose as well, and for refinement purpose. If you want to refine our design, then for refinement purpose, often use some computational tools like MATLAB or Program CC uh, for sketching the accurate root locus plot, right? But for basic analysis and design purpose, the approximate root locus plot is sufficient enough. So the next class will discuss the construction rules, and we'll try to sketch some root locus plots for some given systems. So far what we have discussed, do you have any question?
I joined in late today. Can you please consider my attendance?
কখন জয়েন